Hello everyone, I'm Zhang Pan. Today I'm going to present the topic, the distance between sets. In reality, we know the distance between 2 points, but how can we extend it to our sets? In this topic, we'll study how far two sets from each other and when the distance is positive. Here is the outline of my presentation. It will be organized around one main question. If two sets do not intercept, must their distance be positive? To answer this question, I first introduce the definition of the distance between two sets. Then, I will show two examples to illustrate that two disjoint sets can also have zero distance. After that, I will introduce the definition of a point to a closed set and the distance function. Then, I will say that the distance between compact sets and closed sets. Finally, some application and conclusion will be included. Here is the motivation part. In Rn, distance is very common, like 2 points, 2 lines, something like that, telling us how far two objects are. But for sets, it's really interesting. There are so many points in the sets. So we need to compare all possible distances between these points. And here is one main question. If two sets are disjoint, must their distance be positive? The answer is no, and I will explain it later. Here is the definition of the distance between two sets. Let A and B be two subsets of Rn, and the distance between A and B is shown like this one. And the infimum is the biggest lower bound. However, why we use infimum rather than minimum? Sometimes the closest distance is not actually reached by any 2 points. The points can get closer and closer, but they may never attain the smallest distance. So we use the infimum to represent the distance. Also, if A and B are not disjoint, then the distance between A and B is 0. Since A and B intercept is not empty set, we can say there must exist some elements, right? We can let X be the point in this intersection. So X belongs to A and A belongs to B. Since by the definition of the distance, it's an infimum of some 2 points, so we can let A equals to X, B equals to X. So A and B, the distance between them is 0. So the distance between A and B is 0. Here is the first example. Bounded disjoint sets. We can see that the set A is x squared plus y squared less than 1, and the set B is x belongs to 1 to 3, and y belongs to negative 1 to 1, which is a rectangle. And for x, we can know, since x is belong to 1 to 3, then x squared also larger than 1. And for y squared is also larger than 0. So x squared plus y squared in B is larger than 1. So A and B are disjoint. We can take AK in A like this one, 1 minus 1 over K, and B is 1, 0. So which are all satisfy the condition of both sets. So we can calculate the distance between AK and B, which is equals to 1 over K. When K goes to infinity, 1 over K goes to 0. So the distance between A and B is 0. By squeeze theorem, since the distance cannot be negative, so the distance between A and B is 0. Here is the second example, closed disjoint set. We can see that the set A is y equals to 0 and B is xy equals to 1. Their product is equals to 1. So A and B are both closed sets. And since xy equals to 1, so y cannot be 0. So A and B are also disjoint. Take AK equals to K0 and BK equals to K1 over K. So this product is 1. So BK is in B and AK is in 1. So we can calculate their distance is 1 over K. Similarly, equals to when K goes to infinity, 1 over K is close to 0. So the distance between A and B is 0. So we can see that the closed disjoint set, the distance between sets are also positive be 0. Now we consider a special case. If one of the sets is just a single point, x0, then the distance from x0 to a set A is defined like this one. So this formula, this measures how close the point x0 can get to the set X. Here is one important detail. It is possible that the distance between x0 and A equals to 0 when the point x0 is not in A. If A is not a closed set, we can show an example. Let A be 0, 1, so A is not closed, and x0 be the point 1, which is the limit point of A. So we can choose one point AK equals to 1 minus 1 over K. So which is in A, then the distance between AK and x0 is 1 over K. Similarly, when K goes to infinity, 1 over K goes to 0, so the distance between x0 and A is 0. But we know x0 is just a limit point of A is not closed, x0 is not in A, so this is possible case. Now we have an important proposition. Let A be a closed subset of Rn and let x0 be in Rn. Then the distance between x0 and A equals to 0 if and only if x0 is in A. We'll prove it here. If x0 is in A, then we'll prove this one. We'll prove by contradiction. If A, suppose x0 is not in A, since A is closed, so its complement is open. By the definition of the open set, there must exist one open ball, x0 R, in this open set. Then we know for every point in this ball, x0 minus A is larger than R. So the biggest lower bound is R, and R is larger than 0. So the distance between x0 and A is larger than 0, not 0. Next, we define the distance function. Here is the mapping and here is the function. The distance between x and A. Here is the proposition. The distance function is continuous, and we'll prove it by using triangle inequality. Here is the proof. For any A belongs to the set A, by triangle inequality we can get this inequality. Then we can move this side, the same side, move to the left side, so we can get the distance mu and A minus re and A is less than this one. By interchanging mu and re, we can get this formula. Similarly, we can move this to the left side too. Then we can get this, the absolute is less than this one. So we can prove that this distance function is continuous. Now we come to the main theorem. Let A and C be disjoint subset of Rn. If A is compact and C is closed, then the distance between A and C is larger than 0. Here is the key idea. Since compactness allows the continuous function to attain a minimum, since it's compact, so it is bounded and closed, so we can attain the minimum. Since closed, so we can know the limit point, it contains all the limit point, and bounded, so we can attain the minimum. Closeness makes the minimum positive like we have proved previously. Here is the proof of this theorem. Define this function, mapping, and this function. Since it is compact, we can attain this minimum. However, since it is disjoint, we have already proved the distance must be positive, must larger than 0. So the distance between A and C is also larger than 0. Since the minimum is larger than 0, so the distance between A and C are also larger than 0. And here is one application and the summary. Let A be compact and let U be open with A is a subset in U. Then there is delta is larger than 0 such that we can get this one to imply X is in U. The idea is that U is open, so its complement is closed. Since A is compact and A is a subset of U, so the set A is disjoint from the complement of U. By the main theorem, we just proved, the distance between them is positive, so all points close enough to A must still stay inside the mu. Let's make a summary. The main message is that disjointness alone does not guarantee positive distance. We also need suitable conditions, like closeness, compactness to hold. And here is the reference. Okay, that's all for my presentation. Thank you for your listening.